Good afternoon, everyone. Thank you very much for coming. We have Tim today here. So Tim spent the last few weeks with us, and he will be here until next Friday. I assume that most of you know Tim is expert for defects in silicon. He did his PhD in Fraunhofer ISE, graduated 1 year ago, 2017, and he now work under undefined title, I think, for now, in Fraunhofer in the University of Freiburg. And Tim will speak with us on his expertise, so it's defects in monocrystalline silicon. So it's great to have you here, Tim. It was great to have you in the last few weeks. Please welcome Tim.
Thank you. Thank you, Ziv, for having me. Yeah, I'm going to talk about some results mostly on float zone silicon, so not just monocrystalline, but even the float zone type. And I want to start with introducing where I'm coming from and who's paying me. So Fraunhofer ISE and the University of Freiburg. I guess most of you have heard about Fraunhofer ISE in the field. We're the largest research institute on solar energy in Europe. And we cover the whole range of photovoltaic, solar thermal technology, also building technology, and up until the whole energy system that some groups of us model. About 1,200 employees make us a very large institute. The part where I'm working in is photovoltaics, and there we cover the range from silicon crystal growth all the way to module implementation, and my position is somewhere here in between on the material characterization side. The University of Freiburg, as you might see, it's way smaller than the University of New South Wales. But on the other hand, we're way older, so we have a lot of expertise on being a university, let's say that. And I'm working for the Department of Sustainable Systems Engineering and for the Freiburg Materials Research Center that's also associated with the university. So to science. So I want to discuss some studies that I took part in the last 2 or 3 years on float zone silicon. So let's start with what float zone silicon is. Well, it's a great reference material. That's what a lot of you will have used it for or will use it for in the future, because it has this very high silicon material purity, and that gives us a stable quality for the material, and we wouldn't expect any process interactions when taking a float zone wafer through a high temperature process, for example. Then experiments with a passivated sample. I guess this is a p-type 1 ohm centimeter sample. You of course have some variations in the lifetime that we get. So here's a lifetime plot for 2 samples, and we have some variation with just processing issues. However, this is the next experiment that I did, and we see a very different lifetime level that we wouldn't expect from a float zone wafer. And again, we see this small variation of the process, but the overall lifetime level has dropped significantly. And our technology guys promised me that it wasn't their fault, so they did the same thing as before, which leads to the thought maybe float zone is often not a great reference material. And we dug deeper into that, and we found that other groups had seen that too. So here is a by now quite famous graph from Nicholas Grant, from a paper that he did, where they subjected float zone wafers of different manufacturers to thermal treatments at different temperatures. And as you can see, there is a certain temperature range in which the lifetime just drops. And some of these wafers are mostly dead lifetime-wise. And this temperature range that we're talking about is actually touching the range in which quite a lot of our research is being done. So for example, dielectric deposition of surface passivation layers or anti-reflective coatings is actually in this temperature range. And then there is this high temperature range where also the lifetime is affected by the treatments. So yes, the stable quality is kind of an issue. The good thing is this effect that Nick has been seeing is quite characteristic. So when we take a PL image of a wafer, then they usually look like this. Or of a wafer that's strongly affected by that. So if intensity here is giving us a direct measure of the lifetime, then we see that the lifetime is quite good at the edges of the wafer. There is a good rim of lifetime, and then the lifetime drops significantly, and we have this this sphere shape in the middle, or no, circle shape in the middle of a really bad lifetime. Yes. These defects and also this pattern goes away after high temperature treatment. So we wanted to have a look at this initial material quality. That's basically what I was showing you before with this experiment, or with these two experiments that were just really, or just not giving the same results, and then looking at, hey, can we maybe fix our material by doing high temperature treatments? So here's one of the experiments that we've done. We started with 10 ohm centimeter N-type float zone silicon, full wafers, and we subjected them into a series of different different processing sequences. For example, we took samples and just Pockle diffused them, or we Pockle diffused them and then did an ALD deposition of aluminum oxide. And then there was a sample group that underwent a full oxidation treatment, then a Pockle diffusion, then everything was etched off, and it was passivated with the Ono stack at ANU. And in the end, we want to do lifetime measurements and PL images. However, that doesn't really work when you have so different surfaces. And I mean, these samples here don't even have a surface passivation, so that wouldn't give us information. So what we did is we took images of the sample where it makes sense, of the samples where it makes sense, and then we etched everything back to bare silicon and applied a low temperature surface passivation treatment in cooperation with the University of Warwick. They have the super acid passivation treatment that's giving very good results on the lifetime passivation, and doesn't create or doesn't need any thermal budget for that. So here's some of the results. So the initial wafers just etched back and passivated have a reasonable lifetime, I would say. The lifetime increases significantly when the samples undergo a Pockle diffusion, which is something that you wouldn't usually expect for a float zone wafer, because Pockle diffusion, yes, we all know that it's scattering impurities, but there shouldn't be any impurities in float zone wafers. The lifetime level doesn't change too much with the aluminum oxide deposition. And what we've seen in a lot of experiments, and here this is just one example, is that all the process sequences that were including the oxidation treatment usually gave the best results in such comparison experiments. Here, for example, is a PL image of one of these samples that just underwent a Pockle diffusion. As you see, the bad center, or this bad region in the center, is not as bad as it was before when compared to the rim, but it's still there, still visible, so there is still something limiting our lifetime. And after the oxidation treatment, we see that this is pretty much improved, and this a bit lower lifetime in the center region is quite likely due to these handling artifacts here, or handling damages. So let's summarize some of the findings from this type of experiment that we've done over and over. So we see that in unprocessed wafers, in S-grown wafers that we just take directly out of the box and do experiments on, we sometimes have these defects, and they can affect the experiment that we're doing quite a lot, because the lifetime can be really, really bad in comparison to what it should be and what we would expect it to be. Then we've seen that typical processing does affect the lifetime of float zone silicon wafers. So a Pockle diffusion is actually improving the wafers by or a lot, and oxidation usually improves it a lot. And then there is even some processes that kill your wafers. Basically, I've seen single-digit microsecond lifetimes on float zone wafers. That's not how they should, or how they are supposed to be. The good news is we can deactivate these defects with an appropriate pretreatment, and these wafers then are stable to whatever you do to them afterwards. So once you have done such a pretreatment, you can also go to the temperature range that would otherwise destroy the wafer or the lifetime, and the lifetime will be stable after the treatment. So what I suggest to do for experiments involving float zone wafers is to always have this pretreatment. How we do it is we actually do it for the wafers once we've bought them, and then just store them, and when someone wants to have an experiment, we just use treated wafers from the start. A pretreatment that does work is that you just use any oxidation and then etch back everything and then start your experiments. The one that I would recommend, because it's giving the best results for us, is to combine an oxidation treatment at 1050 degrees with a Pockle diffusion and an etch back that also helps you getting rid of impurities that might be in the material or that you might have caught during the oxidation, for example. Okay, so now we've seen that floats on silicon can be improved, and that and this material can then be used to do surface passivation studies, which is what a lot of people have done with a material that wasn't as stable as it should have been. So we've performed a demonstration study where we just wanted to compare some state-of-the-art surface passivations. So we used 8 different float zone materials, both P and N-type material, different resistivities. They underwent these pre-treatments to stabilize the bulk lifetime. And then we applied 3 state-of-the-art passivation schemes. So an atomic layer deposited aluminum oxide, the Ono stack from ANU, and our TOPCon passivation scheme. Afterwards, we of course did lifetime measurements, in this case with QSSPC and PL imaging. And because it had been shown in the past that passivation layers can be improved further by applying a corona charging treatment, we tested this on this Ono passivation stack in cooperation with the University of Oxford. They have a process that applies stable corona charging, so different to normal corona charging. The charges don't disappear after a while, but they are stable for long times. What we've seen there is that, yes, we get pretty good lifetimes on our material. So here is the 100 ohm centimeter P-type and N-type silicon. As we would expect, the aluminum oxide works a bit better on P-type silicon, while the Ono stack is better on N-type silicon. That's related to the fixed charges that these passivation layers apply. Then we've seen a bit of improvement of the lifetime when we were using this corona charging on the Ono stack. That's what we expected, basically. And the lifetimes that we got out of this experiment on the stabilized wafers are among the highest that have been reached with these passivations and with these materials. However, the great thing is when we look at our TOPCon passivation, so this tunneling oxide passivation scheme that Fraunhofer ISE has developed, and there we see that we reach 95 milliseconds on 100 ohm centimeter P-type wafers and 225 milliseconds on N-type wafers, which is, to our knowledge, the highest lifetime ever reported for floats on silicon, or for silicon overall. Some further results on that. So here with the injection dependence, because these are something like notable exceptions that we've seen. So we get really good lifetimes, and we even get lifetimes that are better than the widely used Richter model for Rougieux recombination. So the effective lifetimes that we're measuring here are actually way higher than the theoretical limit predicts the lifetimes for floats on silicon to be. So the Richter limit is exceeded significantly on these samples of typical resistivities for solar cells. So I mean, the range of 1 to 2 ohm centimeters is actually where a lot of solar cells are being done. So this is also the doping range that's very relevant for modeling solar cell efficiencies, for example. That means that on such materials, on these materials that most people are working on and most people are reporting, for example, surface recombination velocities on, it's not meaningful to do that at the moment with the Richter model, because basically, if we would do that for the TOPCon passivation here, or for the Ono and aluminum oxide on these samples, we would end up with negative surface recombination, which would be great to have, but it's just not physically meaningful. So at the moment, I would say that just using the Richter model to extract your surface recombination is a wrong thing to do. If you are really interested in the surface recombination velocity of a surface or of a passivation scheme, then you really have to go all the way and do a thickness variation. Some more results or some more graphs to put our results into perspective. So here we collected the best reported lifetimes, I think, until 2015, and these points are more recent record lifetimes. also of some, basically of groups that we are working with, and that are also applying such a pre-treatment usually to their wafers. And these points are the points from the study that I was showing you earlier, this demonstration study. And as you can see, on all the materials that we've tested, we are getting world record lifetimes. So this really indicates that this pre-treatment that we are doing to our float zone material is really improving the material beyond what other groups have seen in the past. Okay, now that we have that going, so we know how to take float zone wafers, improve them to what they actually should be, so to very high lifetime, very stable wafers. We have great surface passivation layers. Basically, what do we want to use our float zone for now? It's not the material that you would really make solar cells out of for the production. So what we use it for, or what I've been using it for, is to study defects that are relevant in more common material. Most dominantly at the moment in science is this LeTID defect. So just a short recap on the defect. There is a severe performance loss for multicrystalline silicon PERC modules in the field that has been reported some years ago. And yes, there is also ways to mitigate this degradation in modules. And the lifetime recovers, but it's still a big problem in the industry at the moment. So we were thinking about, hey, how can we use float zone silicon to investigate where this defect comes from? So from a very naive point of view, and I'm not a cell technology person, a PERC solar cell process consists of these steps. So we start with an etched clean silicon wafer. Then we apply a diffusion to that, add some dielectric layers on top and on the bottom to passivate. Then we have a metallization so that we can get current out of it. And then we do contact firing, and it's a PERC cell. It has already been shown in the past that the degradation also occurs on wafers, so not just on solar cells or solar modules. Here, for example, is a result on the effective lifetime of a wafer before and after degradation. So it's not necessary, or in this case, it's even wafers without a diffusion, so the diffusion can be ruled out. That's not causing the problem. Then the metallization is also not the problem because these wafers didn't see any metallization treatment, so we can rule that out as well. Leaving three more things that we can have a look at, so the dielectric layers that need to be deposited. And yes, it has been shown in the past that the presence of silicon nitride layers that are widely used for PERC cells is important for the degradation. And the contact firing has been shown to be very crucial for the occurrence of the degradation. So it has been shown that the peak temperature of the firing process is affecting the degradation a lot. And then, yeah, of course, the wafer could be the problem. So let's look at the wafer first. The degradation has been associated with multicrystalline silicon mostly, and most studies in literature are using multicrystalline silicon because, yeah, that's where the defect was found. However, UNSW and I think mostly UNSW has shown that the degradation, so LeTID, maybe I should spell it out, light and elevated temperature induced degradation, can also be observed in Tucholsky grown silicon. Most of these experiments were done by dark annealing to create the defect, because otherwise the p-type Tucholsky silicon would also show normal light induced degradation due to boron oxygen defects. But yeah, they have shown that it's the same. And then we started using our float zone silicon to look at the degradation, and we see that also float zone silicon can degrade. And here, this is what I mentioned earlier. We can really ruin the lifetime of a float zone wafer by treating it. And in this case, the LeTID degradation has occurred. We see the typical behavior of samples degrading that have been fired, while sister samples that have not been fired with the same passivation stack don't degrade over time. The treatment conditions that we used here are the standard conditions of 75 degrees and one sun equivalent illumination. So yes, we see the same characteristics, meaning that the degradation occurs in all material types, so multicrystalline, Tucholsky, and float zone silicon. We've also tested whether the degradation actually occurs in the bulk. So here you see a comparison of 3 samples at different stages in this degradation. So we have an initial sample, a degraded sample, and a recovered sample, and it was always measured with a typical aluminum oxide silicon nitride passivation stack. Then this was etched off and passivated with the superacid passivation at the University of Warwick. And we see that we really basically get the same lifetimes with both passivation schemes, although we etched away quite a bit of the surface, indicating that it's really a bulk defect. And that it is quite likely caused by the PERC process because it's not there otherwise. Okay, let's look at the impact of the dielectric layers then. So what we see is that, yes, the silicon nitride layer also on float zone silicon, we do need a silicon nitride layer in order to have this degradation. Here you see the comparison of samples where this one sample just had a aluminum oxide passivation layer and was fired with that, and it's not really showing any degradation or relevant degradation, while the sister samples fired at the same temperature show quite strong degradation. Yes, so all passivation stacks, including silicon nitride, show the typical behavior of degradation and recovery. Okay, the impact of the firing step in a solar cell, the firing step would be for contact formation. In this case, it's we're just simulating that because we know that it's important for solar cells. So we take the samples and subject them to similar temperature profiles. So for multicrystalline silicon, it has been shown in the past that the degradation strongly depends on the peak temperature and usually sets in at a peak temperature of 600 degrees C. So when the samples are fired colder, then they don't degrade. This is one of the results that we have had on this. So we see a comparison of 2 firing profiles. One, the black one is a typical belt firing furnace profile that would be used, or that could also be used in photovoltaic industry. And the red one is a profile that we generated in an RTP furnace. And we wanted to simulate the exact same profile there initially, but the RTP process wasn't fast enough. So we compared what the samples are doing after these 2 different treatments with the same peak temperature. And we found out that the RTP processed samples, although they have seen the same peak temperature, just don't degrade, indicating that this difference in the firing profile in the temperature rates strongly affects the degradation. So yes, we've seen that fast firing is necessary in multicrystalline silicon, and there is no degradation for the RTP profile. However, we've seen in float zone silicon quite recently that samples that underwent very similar temperature profiles do degrade, or float zone samples that underwent these profiles, both of them do degrade. We have a slight mismatch with the peak temperature, but also the trend is aligning fine with what we've seen for multicrystalline silicon. So for float zone silicon, we see that the degradation also occurs with the slow firing, which could be quite interesting for the modeling or for the model of the defect. Okay, let's collect some of the insights that we've seen. So yes, the degradation can be present in all material types, further indicating that it's actually a bulk defect and not something related to surface degradation. And the great thing about float zone silicon, I should have mentioned that earlier, well, float zone is a very defined material. There's not too much dirt in it, so especially when you compare it to multicrystalline silicon, where you have structural defects and a lot of contaminations, you just don't know what's happening there and what's moving around or not moving around. While in float zone silicon, there's not a lot of stuff to begin with, so it's way easier to find candidates for the defect, or candidates that play a role in the defect. We think the one important precursor for the defect is introduced during the firing, only when there is a silicon nitride layer intact. We have seen that, or we think that the species needs to be a fast diffuser. I didn't talk about these results in the talk, but we've seen on multicrystalline silicon that there is denuded zones around grain boundaries that indicate that the species needs to be diffused quite fast, and the degradation apparently is directly activated by electrons. As I mentioned, the silicon nitride layer has to be present during firing apparently. And the firing profile is important, and the peak temperature is important, however, not as important in float zone silicon. We think that all of these findings would agree quite well with the suggested involvement of hydrogen, as for example UNSW has been pushing or promoting a lot. We don't really see that carbon or oxygen would make sense with these findings, because there should be way less oxygen and also less carbon in float zone silicon. But despite that, we see quite strong degradation. So we think that because we see the same amount of degradation, or sometimes even more degradation in float zone silicon, that an involvement of carbon or oxygen is not that likely. But we're still searching for the actual defect. With that, I would like to conclude the talk. So in the first part, I was showing that float zone silicon sometimes has problems, and it's not as good as a lot of people are assuming it to be. But that can be solved by just pre-treating the wafers. And once we do that and then use a good surface passivation, we can get record lifetimes. And actually the lifetimes that we would assume, or that we would hope for float zone silicon to have. Yes, the intrinsic limit for recombination, or no, the Richter limit for intrinsic recombination can be overcome, so we do need an update on that. And then I was showing you that float zone is a good reference material for everything that's introduced during the process, because yeah, there isn't too many defects around, so we don't have to rule out all the metals and so on, for example. Yes, so the defect could be caused by hydrogen, maybe in combination with intrinsic defects, or by something that just every one of us or every group introduces to their wafers, but quite likely it's not caused by something that's, or not completely caused by something that's already in the wafers to start with, because float zone is quite pure. Of course, I want to acknowledge our funding agencies and also the colleagues that basically made these results possible and did all the processing and some of the measurements on that. And I want to especially acknowledge the CCPV cooperation cluster that has allowed me to come to Australia and stay here for 8 weeks. And of course, I want to thank you for your attention. And I'm happy to discuss.